welcome to the course on medical biomaterials. We will continue on the topic of mechanical properties of some of the body parts such as tissues, tendons and bones. So, if you look at the stress strain curve for a tendon, it exhibits a non-linear behavior. So, you can see initially this is called a toe portion, that means initially this stress does not increase with strain, but after certain strain it starts increasing and then it behaves in the normal elastic and then the plastic. So, why does this happen? This happens because the fibers gets aligned when you apply a force in the direction of the force. Okay. So, that is why we do not see much tension here, but beyond a certain strain you see the normal behavior of the elastic. So, this highest slope is about 1 gigapascal. This matches with that of collagen. That is why collagen is used quite a lot in many biomaterials, especially if you want to mimic the tendon and other muscles. Elastin has a modulus of elasticity of 0.6 megapascal, tensile strength of 1 megapascal, ultimate elongation 100%. Collagen modulus of elasticity is 1000 megapascal, tensile strength or 1 gigapascal, tensile strength is 50 to 100 megapascal, ultimate elongation is about 10%. So, collagen has much lower ultimate elongation when compared to elastin. If you look at the human abdominal skin, if you look at the stress strain curve, if the force is applied perpendicular to the craniocaudal median, that means if you consider an X-ray entering the head, then if it is leaving the tail, that is called the craniocaudal median. So, it is perpendicular to that, and if it is parallel to that, we have two different stress strain diagrams. As you can see here, the stress strain diagrams are two different. So, if you apply a stress of 1 megapascal, it may have around 25 or 26% strain perpendicular to the craniocaudal, and if the stress is applied parallel, then you may have almost 40% strain. Okay. So, both are very different. Okay. This is called mechanical anisotropy. So, mechanical tropy, because if the load is applied in perpendicular and load is applied to parallel, we will get two different stress strain diagrams, because the tissues are randomly arranged in layers. Okay. So, it extends under small load, because the fibers get straightened and then aligned rather than stretched, and upon further stretching they align and resist further tension. Okay. So, if you look at the modulus of elasticity or the Young's modulus, in the perpendicular direction it will be 52 megapascal, if it is in the parallel direction it is 46 megapascal. Okay. Both are very different. So, depending upon how the tension is applied, whether it is perpendicular or parallel, it will exhibit two different graphs as shown here. If you look at mechanical properties of human tissues, for example skin, tensile strength is very low, 7.6 megapascal, ultimate elongation is 78%, that is before it breaks it can elongate almost quite a lot, actually you can see 78%. Look at tendon, tensile strength is 53 megapascal, ultimate elongation is 9.4. Okay. Heart valve, that is a mistake, spelling mistake, heart valve, arctic, radial, tensile strength is 0.45 megapascal, if it is circumference it is 2.6 megapascal. Okay. Aorta, transverse is 1.1, longitudinal is 0.07, very very low. Cardiac muscle, tensile strength is 0.11 megapascal. Okay. So, depending upon the direction in which the stress or the load is applied, the tensile strength can be different actually, and the ultimate elongation also can vary depending upon how the load is applied actually. This is taken from this particular reference. If you look at a bone, it is made up of many different things like the mineral, which is the apatite, Then we have the organic matrix, the collagen, which is predominantly of the organic matrix, and little bit of other material is also there. So the mineral will be about 69%, that is the apatite. Organic matrix is 22%, out of which 90 to 96 is collagen. Then it contains 9% water. Okay, so this is the composition of the bone. Okay, before it gets dried. Of course, dried, all the water will go away. Then you will have some of these two actually. Calculate the density of the bone. If the density of the organic material is 1 gram per cc and the mineral is that is the apatite is 3.16 gram per cc. How do we do it? We can use the mixture of rules. Okay, so we will assume there is a density of the entire bone is mixture of these two, that is 0.69, okay, into 3.16 plus 1 into 0.22, okay, and then water is also there, so 0.09 into 1. Okay. So the simple mixture rule is density is equal to rho 1 V1, that could be mineral, rho 2 V2, that could be organic matrix, rho 3 V3, that could be water. So 0.69 is the mineral into 3.16 plus 0.22 into 1, 0.09 into 1, that comes to 2.49 grams per cc. So the density of the bone is this. Okay. So depending upon the changes in the ratio of different parts of the bone or different bones of different animals, the density could be varying. Okay. Let us look at the mechanical properties of the bone. Again, these change quite a lot depending upon the type of bone. Okay. Suppose I take the leg bone. Okay. We have the femur, that is here, we call it thigh bone. Okay. Then here the leg portion, fibula and tibia. The modulus of elasticity, this is the difference in modulus elasticity, and you can see the difference in the compressive strength. The femur has a very high compressive strength, whereas the fibula has very low compressive strength. Similarly, arm, the arm here, you have the forearm, so you have the humerus, and then outside is radius, inside is ulna. Again they have some difference in the modulus of elasticity. Okay. And then again there is quite a significant difference in their compressive strength as well. The ulna has the lowest compressive strength, whereas the humerus has the highest compressive strength. If you look at the vertebra, cervical modulus of elasticity is quite small, 0.23, lumbar has 0.16, and the spongy bone, that is the bone which connect with the socket, okay, that has got a very low modulus of elasticity, 0.09. Okay. And the compressive strength also is much lower when compared to rest of the bones. That is why the cervical is a vertebra is a very important region where one does not like to put in too much tension or compression, okay, because of these, as you can see from this data actually. Okay. So the values change quite dramatically. If you look at the bones, we are talking the tensile strength in the range of 120 to 150, whereas when you come to vertebra, it's we are talking in terms of 1 to 3, so almost 100 times less. Okay. Okay, let us look at modeling of mechanical properties of bone, because bone as we saw contains the organic matrix as well as the inorganic material. So it is 2 components. So we have the mineral, inorganic hydroxyapatite, collagen. So we can use the rule of mixtures again for calculating the modulus of elasticity. This is called the Voigt model. Okay. So force, because the force whatever is applied gets distributed on the mineral side as well as on the collagen side. Okay. So as you know, sigma, the stress is equal to force by area is equal to modulus multiplied by strain. Okay. So when we use this and this equation, we end up as the modulus of the bone is given by the modulus of the mineral, volume of the mineral plus EC into volume of the collagen phase. Okay. This is called the mixture. But then the collagen fibers are not distributed in the same direction, they vary in their direction. So there is another model which is taken where f is the fraction of the bone that conforms to the parallel direction and 1 minus f is the rest. So if f is equal to 1, then this will become the Voigt model actually. So we can say a fraction which conforms in a parallel direction, so that follows Voigt model, whereas the remaining portion does not follow the Voigt model. So we can get the modulus using this equation, or we can get the modulus using this equation. This is the simple rules mixture whereas this considers part of the fraction is in the parallel direction, rest of it is not in the parallel direction. Okay. These type of equations are very useful if we want to calculate the modulus of blends or modulus of bone, which is a mixture of many different material. Let us look at one problem. This is the bone, it contains 28% organic, 78% water, 78% mineral and 10% water. The density of organic is 1 gram per cc, mineral is 3.2 grams per cc, water is 1 gram per cc. Modulus is 10 gigapascal for organic, 100 gigapascal for mineral. When we say mineral, it is apatite, and when you say organic, it is collagen, and 0 modulus for water. What is the density of the bone? We can use the mixture rule, we did that problem before. Okay, so we take those ratios, multiply by the corresponding densities and add up, quite simple. So rho is equal to rho 1 V1 plus rho 2 V2 plus rho 3 V3. So 0.7 into 3.2 plus 0.2 into 1 into 0.1 into 1. So the density is 2.54 gram per cc. Okay. Now what is the strain, percentage strain on the organic phase if the bone is strained 0.1%? Assume that the two phases are the same arrangement. Okay. So what is the strain? So these strain will get distributed according to their weight. Before that, let us do this. Calculate the modulus of the bone, assume they are arranged parallel to the loading direction. So obviously we can use the Voigt model. So 0.2 into 10 plus 0.7 into 100 plus 0. Okay. So that comes to 0.7 into 100 for the mineral, 0.2 into 10 for the organic, and 0, that gives you 72 gigapascal. So the modulus of the bone is 72 gigapascal. So mineral of course contributes maximum, that is because it is 78%, organic and water of course does not contribute any number towards the modulus. Now what is the percentage strain on the organic phase if the bone is strained 0.1%? Okay. So total we have is 0.9, we have the organic is 0.2, okay, mineral is 0.7, okay. So so this gives you 0.077% for the mineral phase, because we have taken mineral 0.7. So for the organic it will be the other way, so we put it as 0.2 divided by 0.9, okay. So that will come to 0.023. So the percentage strain for the organic will be 0.023. So for the organic, so it will be 0.1 minus 0.077, that will be 0.023%. Okay. Now let us go to composite. Composites are almost like blends. So composites, we can make composites of two polymers, composites of a polymer and an inorganic material like glass, okay, like we have the glass reinforced polymer, or we can have fibers, fiber reinforced polymer, or carbon reinforced polymer. We can have two metals combined, or we can have an ceramic and a metal combined together to form a composite. So we can have different material. Even your bone is a composite, because we have the hydroxyapatite and the organic phase the collagen. So, typically you can have see the matrix and the inclusion could be, sometimes they use glass beads, sometimes they use fibers, sometimes they use carbon, sometimes you can use another polymer in different shape and size. So, these composites also can exhibit modulus of elasticity, but there are slight challenges here, because the way these the inclusion material is aligning towards the load will have an effect on the tension as well as on the modulus actually. Like we talked about for the skin here also, or we talked about for the previous example, if they are aligned parallel or if they are not aligned parallel, you can have two different situations, right. So, same thing can happen on the composites also. Okay, we will look at that. Okay. So, mechanical properties of composites. So, it consists of say like particles or fibers, like fiber reinforced plastic or glass beads reinforced plastic, or your bone, like I said, is a composite. So, and we have the continuous material, that is called the matrix. Okay. So, I could be the inclusion material, M could be a matrix. So, we can use the Voigt model, E is equal to EM VM plus EI VI, that is VM and VI, or the volumetric properties, volume of the matrix and volume of the inclusion complex. Generally inclusion complex may be 5%, 10%, 20% and so on. So, this is the Voigt model. It is applicable when the load is like this, it is parallel. Whereas, if the inclusion material is perpendicular, then we are in trouble actually, like this. Okay, inclusion material is perpendicular, then there is something called the reuse model, okay, where you say E is equal to 1 by Vi divided by EI, that is for the inclusion material, plus 1 minus Vi divided by EM, that is for the matrix material. So, Vi is the volume of the inclusion material, 1 minus Vi is the volume of the its volume fraction, sorry, its volume fraction of the matrix material. Okay. So, here these V's are volume fractions. Okay. So, these are the upper and lower bounds for E value. So, if you are not very sure what to calculate the E for a blend, okay, the best thing is to use both the models and you will get two values, and your answer, real life answer, will be between those two. Okay. So, that is a good way. So, Voigt model, you use it if the load that is applied is parallel, whereas you use the reuse model if they are perpendicular. Okay. Okay, let us look at a problem here. Imagine we have a stainless steel, a circular cross section 316 L with 1 mm radius and a length of 4 mm. So, it is a rod, stainless steel rod, which is quite normally used especially in orthopedic implants. Okay. And it is coated with 1 mm thick coating of titanium. Okay. Titanium is very biocompatible and bio-inert. So, titanium is very good for such purposes. So, it is coated with titanium. If you look at the stainless steel, the modulus is very high, 200 gigapascal, titanium it is 100 gigapascal. Yield strength of stainless steel is 400 megapascal, yield strength of titanium is 200, density is 7.84 grams per cc, density is 2.7 grams per cc. Now, I want to calculate properties of this particular okay, composite material. So, volume of stainless steel, it is a circular rod. So, 3.14 in pi r square height, right. It is 1 mm radius. So, 1 square into 4 and that is the height. So, it comes to 12.564 millimeter cube. Volume of titanium, now this is like a tube here. Okay, the inner radius is 1, the outer radius is 2, tube, outer radius of 2 mm, inner radius is 1 mm. So, pi into r square minus r square, 2 square minus 1 square into 4. So, this is 3, 12, so this is 37 millimeter cube. Okay. So, the volume of the stainless steel rod is 12.5 millimeter cube, the volume of the titanium tube like this is 37 millimeter cube. Okay. Now, volume fraction of stainless steel. So, what you do? You take 12.56 divided by this plus this. Okay. So, this is 0.25. So, volume fraction of titanium is 0.75. So, density of the composite 0.25 into 7.84 plus 0.75 into 2.7, 3.984 grams per cc, that is the density of the material. So, as you can see, it is more like a titanium because the volume of titanium is very high, and you are using volume fraction in this model. Okay. What is the Young's modulus of the composite? Okay. So, we know the Young's modulus for stainless steel is 200, for titanium. So, we use the okay, the normal equation, if you remember. Okay, White model E is equal to EM Vm plus EI Vi. So, we use that, and 0.25 into 200 plus 0.75 into 100, we get 125 gigapascal. This is the Young's modulus of the composite. If the composite is loaded in the longitudinal direction, what will be the yield strength? Again, we know the yield strength. Yield strength is 400 and 200. We can use the same White type of mixture rules, 0.25 into 400 plus 0.7 into 200, 250. Now, how much load it can carry without plastic deformation? So, we have to be careful because load is applied. So, we have the titanium, we have the stainless steel. Okay. So, the total cross sectional area is 3.14 multiplied by 2 raised to the power 2. Okay. How did you get this? So, we have 1 mm here, another 1 mm here. So, the radius of the total thing is 2 raised to the power 4, that is 12.56. Now, load is yield strength into area. Yield strength is okay. What is the yield strength? 250. 250 into area is 12. So, that comes to 3,141 Newton. Okay. Okay, that comes to 3,141 Newton. Okay. So, from there that is the load it can carry without it undergoing plastic deformation. Okay. So, we saw a lot of interesting problems and lot of systems today. Basically, we were focusing on blends. Okay. We are looking at composites, because your bone is made up of a composite situation. We have the mineral and we have the organic collagen, and some in implants many times we use composites or blend type of material, polymer blend. Sometimes we use polymer, inorganic material composites, sometimes metal combinations are used. Okay. So, we looked at how to calculate the density of the blend or the composite, how to calculate the modulus. We can use the rule of mixtures, or we have different type of model available. Especially this situation comes if the inclusion material, whether it is parallel to the load that is applied or whether it is not parallel. A fraction of it may be parallel. So, for that fraction we may be able to use the mixture rule, but remaining portion we will not be able to use the mixture rule. So, we have slightly different models coming into focus. So, the blends always will have this type of problem. So, if you have two different materials having two different properties with respect to density, tensile strength and modulus of elasticity, the properties of the overall material is going to drastically change. So, when you design biomaterials, we need to keep that in mind. This happens in our bone, which is a composite of both hydroxyapatite, okay, and collagen. That is the one is the mineral, that is the apatite, and collagen is the organic phase. So, both of them have different modulus of elasticity. So, the bone properties also changes quite a lot. And I also showed you very interesting data on the modulus of different types of bones. We saw that vertebra bones have very low modulus, almost 1/100. Another interesting point we saw is the way the load is applied if he has the skin of the stomach, the way the load is applied in whether it is longitudinal or whether it is in the parallel direction, the stress strain diagram can be very different, and for a given stress the percentage elongation can also vary. So, we will continue in the next class on some more properties related to biomaterials. Thank you very much for your time.